In this series of videos, we will be using the derivative to find the maximum and minimum values of a function. In this lesson, we will be looking specifically at the first derivative test.
All right, hi everybody. So here we're going to take a look at the first derivative test. Okay, so in a previous lesson we looked at what a critical number was, we looked at intervals of increasing and decreasing, and the inclusion of the endpoints and whatnot when the derivative is positive, when it's negative, and so on. Now we're going to put some of that stuff together and use it to make some very specific conclusions about what the function is looking like. Now actually, really what we're going to do with this is just give a name to an idea that you're probably already aware of. You've already probably pieced this together. Whoops, wrong way. So to start off with, just remember that if a function f has a local maximum or minimum at c, at some value x equals c, then c must be a critical number of f. Okay, and bear in mind what that means. Okay, that means either f primed at c is equal to 0 or f primed at c is undefined. Now, that does not mean, that just because f primed at c is equal to 0, f primed at c is undefined, just because that c is a critical number does not mean we've got a maximum or a minimum there. But if we've got a maximum or a minimum, it must be at a critical number. Okay? So the relationship isn't necessarily two-way. Okay? So just be aware of that. So if you've got a max or a min, then you're definitely looking at a critical number, but just because you've got a critical number does not mean that what you're looking at is a maximum or a minimum. So how can we tell? Well, we've got something here called the first derivative test. So let c be a critical number of a continuous function f. So now we know right now that for some function here, f primed at c is going to be equal to 0 or f primed at c is undefined. So that's given in this particular little analysis here. Now, if f primed changes from positive to negative at c, okay, if the value of the derivative goes from positive on one side to negative on the other, then we can conclude that f has a local maximum at c. And that should probably make sense, because in an interval where the derivative is positive, we've already seen that that corresponds to an increasing interval. Okay, so what we've got here along the number line here, here's our value c. That means to the left of that, the function's going up. It's a critical number, so we know the derivative will be 0, so it levels out. And then to the right of it, since the derivative is negative, we know that that typically corresponds to a decreasing sequence. So it goes up and then comes back down again, which means that that point right there that we were looking at is a maximum. And specifically a local maximum, remember, because we can approach it from both sides. And that's key if it's a local maximum. And that's what we're talking about right here. Rules are a little bit different at endpoints. Now, on the other hand, if the derivative changes from negative to positive at c, then f likely has a local minimum. They're not likely, we know it does. So here's what we've got. We've got c here. We know to the left of it, the derivative is going to be negative, meaning the function is decreasing. We hit a point here where the slope of the tangent is 0. That's our critical number. And then to the right of it, we know that the function is on an increasing interval, which makes c, x equals c, the minimum. And now finally, it is possible, okay, it is possible that these don't happen even though c is a critical number. So if the derivative doesn't change signs at c, then there's no maximum or minimum there. And I hope that makes sense to you, okay? If I've got a maximum, and bear in mind that we always read graphs left to right, okay, I'm always reading it left to right. So if I go up and then come down, that critical number right there, that's a maximum. If I come down and then go up, that critical number there becomes a minimum. That's the only way that can occur. I can't come down to a maximum. Okay, I can't go up to a minimum value. Okay, but it is possible. Okay, it is possible that I drop down. I hit a point where the derivative is either 0 or let's say undefined, but then I keep dropping. So it could be an inflection point. In fact, that's very likely, particularly in the context of this course, that's very likely what's going on. So let's say, for example, I hit an interval here where I drop down, I hit a spot where the derivative, okay, where the slope of the tangent line is 0. But then on the other side, it keeps dropping down, like it does with a cubic function. Okay? Well, that point right there is not a maximum or a minimum. It might be a critical number, but because the direction that the function moves doesn't change, it's not. In fact, it's a point of inflection. Now, another way that this could occur is you could have a function that does something like this. It's still decreasing, goes like this, and then drops down like this. Now, in this particular case here, okay, this value right here would be a critical number because the slope of the tangent is undefined. Here, the slope of the tangent is 0. Here, the slope of the tangent is undefined. Again, notice that it's decreasing to the left, decreasing to the right, but the concavity has changed. Okay, the type of curvature has changed. We're going to talk more about that later on here. If you've looked at other lessons, you've seen or heard references to the curve sketching and concavity already. But anyway, that's the sort of thing that we've got here. This little thing becomes a point of inflection, just like it is here, point of inflection. But two different types, because here the critical number is due to a 0 as the derivative. Here it's due to an undefined. Anyway, that's not really our focus in this particular lesson. Our focus is this. Using that first derivative test, watching it go from positive to negative or negative to positive to determine maximum or minimum values. And that's really, really a powerful tool to have. Let's take a look at some examples. All right, now in this example, it says find the maximum and minimum values of this function, okay, 3x to the 4 minus 16x cubed plus 18x squared plus 1. Okay, now that's a pretty complicated looking function there, polynomial function. Now, you should probably know roughly from previous courses what this function looks like. It's a quartic, okay? So it's going to have that kind of characteristic kind of W shape, sort of. I mean, it opens up, we know that, so it's going to come down. It's going to have 2 or 3 turning points at most. Okay, go back up again. Usually in one of the previous courses that I would teach here prior to a calculus course, we would spend a lot of time looking at how this function behaves around the x-axis. But now due to calculus, we can spend a little bit of time looking at how it behaves away from the x-axis. Specifically, we can look for these maximum and minimum values. So we're going to use the first derivative test, but what that means is we got to take the derivative. And actually what we're going to do first, our number one thing that we're going to do is we're going to look for critical values. Okay, critical values of the function. So we're looking for places where the derivative is 0 or undefined. So first of all, let's take the derivative, and that will be 12x cubed minus 48x squared plus 36x. Okay, now I already know, because I can tell this is a polynomial, I know that this isn't going to be undefined anywhere. So I don't need to worry about looking for those kinds of critical numbers. However, I do suspect that it will be equal to 0 in one or two places. First of all, I notice that there's a 12x common to all of those terms, and that's going to leave me with an x squared, okay, minus 4x plus 3. And then that's a quadratic that I can factor. X squared can be rewritten as just x multiplied by x. Now I know that positive 3, and I love this about having primes in there, I know positive 3 can really only be broken down into the two factors 1 and 3. The fact that it's positive 3 means they're both the same sign, okay? And the fact that the middle term here is negative means that these are both negative. So that was a really easy one to factor here. So now I know that my critical numbers, okay, or my critical values are x equal to 0, 1, and 3. Those are my possible maximum and minimum values. Well, now I'm going to look a little bit closer into this. Now, I've got my derivative right here, and the beautiful thing about this is I've done some work. I know my x-intercepts of the derivative. So what I'm going to do here to investigate this, I'm going to look at what the cubic looks like, okay? And I'm going to use the information that I glean about this cubic function to tell me how this function behaves. Now that can get confusing for people. You're going to need to really bear in mind what we're doing. This is the function we are analyzing. But I'm using the derivative as a tool for understanding how this function behaves. So when I discover the intervals where this function here, the derivative is positive, that means this function is increasing. Where this function is negative, that means the original is decreasing. So that's what I'm looking for here. And I know that this function is going to go to 0. At 0, we'll do it like this, 1 and 3. Okay, I know that this is a cubic, that's positive, which means it's moving up. Each one of these roots has a multiplicity of 1, so that it's going to pass right through. So my derivative function's got to look something like this. It's got to go up, turn around, come back down, go back up. It's got to look something like that, which means it's negative over here, positive here, negative here, positive here. Now, bear in mind that there were two parts to this discussion here, okay? So I know that the derivative is less than 0, okay, on the interval negative infinity up to 0, not including, union 1 to 3. That's where the first derivative is negative. The first derivative is positive on the interval 0 to 1, union 3 out to infinity. And notice I'm not including the endpoints here because the derivative goes to 0 at those endpoints. But that has an implication, okay? That has an implication as to how the original function up here behaves. So because the first derivative is negative in this interval, positive in this interval, I know that f of x decreases, okay? It's going to decrease on the interval negative infinity up to 0 inclusive. Okay, because remember what decreasing was. When we talked about decreasing and increasing, we need to have, it's always with respect to 2 points. Okay, just having the derivative become negative is not enough. There was a little bit more to it than that, which allowed us, or no, didn't allow us, basically kind of forces us to include that endpoint. Union the interval, the closed interval from 1 to 3. That means f of x increases on the interval 0 to 1, union, and 3 to infinity, including the 3. Now remember, we're not including the infinities here because those aren't real numbers, so that doesn't really mean anything. Okay, that's just an indication that we continue to go on and on and on in those directions. Okay, so what does this mean? Well, let's take a look right here. That means that before the 0 I drop, after the 0 I go up, which means that's got to be a local min. So we know that we're going to get a local min at x equal to 0. And if we go look that up, the minimum value is going to be f at 0. And if you plug that in, you'll get that that's equal to 1. So there's our minimum value, our local minimum value. Okay, so this right here is our local min value. That's what the question was actually looking for. 1, well, we're increasing to the left of 1 and decreasing, so we're going up to 1 and then coming back down again. That makes that a local max. Okay, and then if I plug 1 in to our original expression, now remember, not into the derivative, you got to go back up to the original to get that value there. If you plug 1 into that, here we're going to get 3 minus 16 plus 18 plus 1. I believe you get 6, which is our local max value. And then finally, we've got this 3 here, and we are decreasing to the left, increasing to the right, which makes that a local min at x equal to 3. And if we plug that in, f at 3, I believe we get negative 26, and that makes that our local min value. Now, if we plot this, okay, we can go just a little bit further. Okay, if we plot this, here's my 0, here's my 1, and then here's my 3. I know that my function is decreasing, so it's going to come down to 0, 1, goes up to 1, 6, then it comes down to 3, negative 26 here. This is a local, okay, this was a local min, so it's got to do this. This was a local max. This was a local min. So my function had to look something like this, And if you go to your calculator and play with it a little bit, yeah, you'll see that it looks something like that. So this one right here, actually, we could have gone one step further with this because this is a polynomial. We know it's a smooth function. It doesn't have any asymptotes in it breaking it up here. When I compare all these, I know it's a quartic that opens up. This was my lowest min. This is also my absolute min. Okay, I could have made that judgment there at that point too. All right, there we go. All right, now for this question, we read, find the maximum and minimum points of the function f of x is equal to 3 minus 1 over the square root of x squared plus 1. Okay, now, as soon as I see that radical in there, and particularly when I see something, when I see a value of, or sorry, the variable x in the denominator, this suggests to me the possibility of there being issues with the domain. And remember that critical numbers are only defined in the domain of the function. So I really should check the domain, okay? I really should check the domain of f of x first, because this could tell me whether I've got critical numbers or not. Now, when I take a quick look at this, first of all, to keep all my values of x real, I can't allow the radicand to become negative. But actually, it never does. X squared plus 1, if you think about that, x squared plus 1 is a parabola that opens up above the value of y equal to 1. So it never actually does become negative. So turns out that is there's no restriction introduced because of the radical. Okay, well what about because of the rational, the 1 over? Does the denominator ever become 0? And again the answer is no, because the radicand never gets to 0. Okay, the square root of 0 is 0. But this value here never gets to 0, so it turns out that actually my domain is all reals. It's kind of nice. It makes that easy to work with. So any place where I see my first derivative becoming undefined or going to 0, those will be critical numbers. Which leads us to the next step here. Let's take the derivative. Okay, well, the 3 becomes 0, so that's okay. Now we've got the negative 1 out front, right there, and I'm going to separate that out. This all could be rewritten as x squared plus 1 to the negative 1/2. Okay, so in my head I got to see it like that right there. So I will bring down the negative 1/2, and this will become x squared plus 1 to the negative 3/2. And then the chain rule tells me to multiply by the derivative of the interior function there, so that's going to be 2x. Okay, so I've got a negative of a negative that's going to become positive. I've got a 1/2, but over here I've got a multiple of 2, so those will cancel. And I'm left with x over the square root of x squared plus 1 cubed. Okay, so there's my derivative. Now, I am interested in the values where the first derivative goes to 0 or is undefined. Now, let's just talk about where it's undefined first. Now, notice I've got x squared plus 1 down here. Okay, and we mentioned this with the original function because look at the denominators are roughly the same, other than the fact that this is cubed here. It doesn't go to 0. So the first derivative is never undefined. So that's not the issue here. However, it does go to 0. Okay, so f prime of x is equal to 0, where the numerator goes to 0, and that's going to be where x is equal to 0. So that's kind of convenient. Now we should just double check that that doesn't lead to 0 over 0, although in this case I know it won't. But that is something that you should be aware of. If you plug 0 into the denominator, okay, it doesn't cause me a problem there. It stays 1 down there. Good. So there's my only critical number right there. X is equal to 0. Now, let's take a look at what happens along that number line. Here's 0, and we're interested in what's going on with the first derivative. Okay, well, when I look at the expression here for the derivative, notice that the denominator, any value of x that I plug into this, whether it's positive or negative, x squared will be positive. I increase that by 1, it's going to be positive. If I take the square root and cube it, or cube that number and square root it, it's still going to be positive. In fact, the only thing that will determine whether it's positive or negative, that derivative, is the value of the numerator, which is going to be negative to the left of 0 and positive to the right of 0, because that's just where those numbers occur. So, f primed of x is less than 0, okay, on the interval negative infinity to 0. F primed of x is greater than 0 on the interval 0 out to infinity. But that implies that the original, I'll just do it like this. The original function is decreasing, okay, is decreasing on the interval negative infinity to 0 inclusive, and is increasing on the interval 0 to infinity. And again, we're including the 0 there. So because the 0 is included in both a decreasing and then increasing intervals, okay, we're dropping down and going back up here. We know, therefore, that at x equals 0, we get a local minimum. Okay? Now, f at 0, if I plug that into the original function, and bear in mind, I got to go right back up to the original function. If you plug 0 into that, well, 0 squared is 0, plus 1 is 1, square root of 1 is 1, 1 over 1 is 1, 3 minus 1 is 2. So f at 0 is equal to 2. This becomes our local minimum value. So what's the point of that local min? Well, we've got a local min, and its coordinates are 0, 2. But now, just before we wrap up this question and even this little lesson here, bear in mind that this is the only minimum that we've got. Okay, from negative infinity to 0, this thing drops, and then from 0 out to positive infinity, it goes up. So not only is that a local min, it's also an absolute. Oops. It's also an absolute min. Okay? I hope that makes sense. In subsequent lessons here, we're going to start to look at all sorts of different word problems that utilize this idea, the first derivative test, to find maximum, or to help you maximize and minimize the values of certain functions.